Good morning, ladies and gentlemen. Today we'll be doing some measurements of dispersion of ungrouped data. Now, we will focus on range deviation from the mean, what it means to deviate from the mean absolute deviation, the variance and standard deviation, the coefficient of variation, skewness, and Chebyshev's theorem. Our lecture for today will simply focus on the range deviation from the mean and mean absolute deviation. This is how far we will go for today. We'll only do range deviation from the mean and MAD. We will do variance and standard deviation in another lecture. So, the range is basically the difference between the maximum and the minimum value from the observed value. You need not to actually arrange them, but if you arrange them, it's still up to you. But all that's important is the range is maximum minus minimum, which is what we are given in the formula. To calculate when you are told to calculate the range, or when you want to calculate the range, you're basically just trying to find out how far apart are the minimum and the maximum. When you say how far apart, for instance, you may have the smallest number being 1 and the largest being a million, which means there's a huge gap between the smallest and the largest. But you may have 1,000 values, only to find out that those 1,000 values, they are between 1 and 20. So that even though they are a lot of values, but the range between the maximum and the minimum is very small. So we just want to know how dispersed, hence the word dispersion. We just want to know how dispersed are they from between the smallest value and the largest value. Now the smallest values, they could be many small values as long as they are all the same. For instance, if the smallest value is 1 and you have 12 ones, it doesn't really matter which one you take as long as you take that smallest value. If there are many small values that are equal, then you take any of them. And then with the range, we have what we call the mid-range. The mid-range is just basically the range over 2. That's what it means. It's just the range over 2. So we're going to take an example. So below are orders of a supplier of bread for 80, 600, 600, 600, 760. Now, we want to calculate the range. And it's simple. We simply do this maximum minus minimum. We don't care about the values in between. The range doesn't really care about outliers. It just simply cares about what is the maximum, what is the minimum. If it so happens that, of course, the maximum, most of the time, if there is an outlier, the highest value will be that outlier. So the range, it may use the outlier if the outlier is the maximum value, which of course basically tells us that we cannot actually trust the range as much, but it does give us an idea of how vast or how far apart the smallest and the largest value is. So the maximum value here is 760. So if it's 760, the minimum value is 480. We don't care about the 600s. We just want to know what's the maximum, what's the minimum, and then we subtract these two to get 280. So the range of this particular data is 280. Now, we go to deviation of the mean. Now, to understand deviation from the mean, we need to actually first understand what we mean by variability. Now, variability refers to the extent to which the values in the data set vary around, that is, differ from the associated measure of central tendency, which is normally the mean. Now, what it means is, in simple terms, we just want to know how far apart are the values from the mean. So deviation, of course, deviation is the term that we will use, or dispersion, in other textbooks they will use that term, is variability or variation. That is, how far apart are the values from the central point, which of course that central point is the mean. The mean is the one we calculated in the previous video. Now, deviation, of course, in particular, is now the measurement of how far the values are from the estimated value in general. Now, when you talk about deviation, now we want a single measurement such that that single measurement tells us on a general scale how far apart or close are the values from the mean. Remember, the mean is a central point. Everything, the mean takes into consideration all the values. So the mean becomes the central point. Now deviation just wants to know how close are they to the central point, or are they scattered apart? Now this measurement, which is of course deviation, now the measurements of course will differ, but this generalized measurement, which is deviation, gives us an idea of how far apart the values are from the mean on a general scale. So now we'll focus on the population mean, which is mu, and to understand it, now we'll need to consider the data below. Say we have every value being the same. In our example, we've got 1. So we've got every value being the same. All the values, every time you look at the observation, it gives the same thing. Every time you look at the observation, it gives it the same thing. Now, we have these 6 ones. All the observations are 1. So the mean, and remember we said we only consider the population mean. The mean is now 1 plus 1 plus 1 plus 1 until you reach the last one. And 6 ones will give us 6, and 6 over 6 is 1. Now, what does this mean? It means the mean is a perfect describer of the values. Now, the role of the mean is to be able to give us an idea of the values we are to expect in the data. That is the role of the mean, is to give us an idea. So when you look at 1, if we have not seen the data itself, or if we've not thoroughly analyzed the data, when we look at the mean 1, we expect values that are somewhat around 1, maybe 2 or 3, but not too big. Maybe half and quarter, but not too big as like -3 and -2. So we expect values that will be closer to 1, not necessarily 1. But what in such situations where the mean is the same as every other value of the data, now the mean is a perfect describer of the data, because the mean is supposed to describe what the data is supposed to be like. What kind of values should we expect in the data given? Now we're going to, looking at the data that we have, now we're going to change it a bit. So since we say that the mean is the perfect estimate of the data, that is, it perfectly tells us the values that are there in the data. Now, When you find the difference, of course, that is the mean. Now this is where the deviation comes into play. How far apart are the values from the mean? Now, when you observe this data, if we were to subtract the mean from each and every observation, as we see here, we subtract each and every, that is the value minus the mean, the value minus the mean. If we were to subtract each and every value from the mean, this is what we have, showing how perfect the mean is, what a perfect describer it is of the given data. So basically, there's no difference between the mean and the values because the mean is the same as the values in the data. Now, if we were to change one of these values, let's say 2, to 2, sorry, the data would then be 1, 1, 2, 1, 1. Now, not all the values are the same. Now we've got all ones, then we have a 2, and then all ones again. Now, we do expect some changes from the value of the mean, but we don't expect too many changes. So when you calculate the mean, this is what we have. Now, we no longer have 1. We have 7/6. Now, 7/6 is, if we were to use our calculator, it's 1,1666666, meaning it's not so far from 1, but now it's no longer a perfect estimate. It doesn't mean it's a bad one, because 1,1 or 1,2, when you look at the mean to be 1,2, we expect values to be around 1, not necessarily 1 as we see in the data, but somewhere around 1, maybe 2, maybe slightly above 2. That's why when we look at the mean, it's supposed to give us an expectation of the type of data we are supposed to receive. So now, looking at the difference, now we see that there are no longer zeros because the data, all the values in the data are not exactly the same as the mean. It doesn't make the mean a bad estimate. It just simply says that now there is some variability. There, in the first example, there was no variability because the value of the mean was exactly the same as the data. Now here there is some variability. It's very small, but it's still there. Now, in most cases, we will never, no, I shouldn't say never, but rather it's rare to find zero mean. The mean can be a small, very, very close to zero, especially when you're dealing with small numbers like atoms, or small numbers like a change in percentage of the stock prices or the markets. So we can expect small values there, but when we're dealing with large numbers, we cannot expect the variance to be as close as zero. But it doesn't mean a large variance is a bad variance. It just simply means that you need to observe the data and see. But there are measurements that we are going to deal with, especially when we go with coefficient of variation. There are measurements that we use to assess how much of a variance or how much of a deviation is there from the mean. So now, going back to this, now we've got a negative 1,6 on the first three values, 5,5 on the fourth, and then negative 1,6 from the last two. Now, meaning there is some variability. Now, yes, the dominating value is negative 1,6, but that doesn't actually, it's not really a factor as such. What's a factor here is that we no longer now have a zero difference. The fact that we don't have a zero difference, it means they are not in the same spot as the mean. They are not all in the same spot. Maybe one or two are, but they are not all in the same spot as the mean. There is some variability, meaning they are scattered around the mean, very close to the mean, yes, but not on the same spot as the mean. Now let's take these sets of data. We've got the first data is 7, 8, 10, 12, 16, 16, 20. Second data is 7, 8, 9, 10, 11, 12, 13. Third data is 900, 902, 904, 906, 908, 1000, 1002. Now the first one is just, it's increasing, but it has no particular, it has no particular pattern. The second data, it increases by 1. Third data uses much larger figures, but it has a consistent increase of 2 of the previous value. Now we'd like to know the difference between the mean and their respective values, the values of each data. Now, what we want to know is there, first of all, a difference between the values and the mean? One. Secondly, if there is a difference, how big of a difference are we talking about? Just because the values are big doesn't mean the difference in mean is expected to be big as well. So let's look at it. We take the first data. The difference is negative 40 over 7, negative 23, negative 19. There is a difference, but the difference is not that much. But when we look at the second one now, it's negative 3, negative 2, negative 1, 0, 1, 2, 3, with a mean of 10. As much as they were almost equal with the first value, or they were not far apart, but the difference from the first data is much larger than the difference of the second data. But when we look at the third data, now there is a huge difference in figures. Because of course, as expected, the values are very large. We're talking about 900s, 900 and 1000. It is expected that the values are large. But the fact that we see that even though the values are large, but they are not that big. As for instance, 496 when you convert it into decimals, 492 when you convert it into decimal, it's actually 70. It doesn't go as far as the 900 and 800 that was given. The difference is actually 70, which is smaller than what the actual values that we have. So the difference did not necessarily be big just because we deal with large values, meaning the deviation need not to be big just because we are dealing with large figures. So we go to our last part for the today. Now, we said that the point of deviation is to assess how far apart are they. Now, before we go to the mean absolute deviation, I would like to give a small sketch. Now, when we talk about deviation, this is what we mean. So, let us say you've got all these points. This is deviation. Let us say you've got all these points right here. And let us say you've got another one right here. And then you've got another one right here. Now, these are 3 different points. Let us say the small black dot here, right at the center, is the mean. Now we see here that these values, they are much further from the mean. We notice that they are much further from the mean, meaning there is a lot of deviation when you look at this observed data. Remember, we said the mean is theoretically the central point of the whole data because it takes into consideration all the values that exist. Now, when you look at this one, yes, there is some deviation, but there is little deviation. Yes, the deviation is there, but when you look at the circle, it's actually quite smaller, meaning they are very congested towards each other, towards the mean. And then when we look at the last one, the deviation is so small, it's almost non-existent. Now, the difference between these two is they all have means, they all have deviations, but the deviation here is much larger than the deviation here. And the deviation here, as much as it is smaller than this, but it's still larger than this one. So if we were to find a mean would be the most perfect if it were to be as close as possible to all the values, meaning the mean becomes the expectation, your expectation of the data. This is what the mean is what you are expecting to see when you look at the data. So for instance, let's say that the university says the average pass rate of the students is 52%, meaning we may have those students that are around 60, 70, maybe even 80, but the majority of the students are around 50, meaning 53, 54, 49, 48, maybe even 31 and 28. But those that are too far away, when we hear the word 52% average, what we put in mind is we expect the data to be somewhere around 52%, meaning a majority of students should be slightly lower than 52 and slightly above 52. The majority, that is the expectation. That is what the mean is supposed to represent. So now when you look at deviation, we just want to know how far are they? Yes, we expect the mean to be central. Yes, like this. But we also take into consideration that there are those that are like this will be very close, and there are those that are like this one, which will be very far. Now we want to know how far are they from the mean. That's what we mean when we talk about deviation. Now, when you look at mean absolute deviation now we are looking for a single measurement. A single measurement, now remember I said if you have no deviation, you will have zero. It's rare to find, if all the values are not the same, you will not have a zero. You will not have a zero deviation. At least one of them is not in the center of the mean. So it is taken out. Now, when you look at the mean absolute deviation, now it gives us a single calculation that tells us how far apart are the values from the mean. Now we have to take into consideration each and every value and sum them up. Basically, what we're saying here is we want to calculate the difference from here to here, 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 the difference from this point to this point, the difference from this point, and then we take all these differences from the center to each point and we add them up. If those differences are too large, then we may conclude to say that there is a lot of variability or there's a lot of deviation. But if we sum these differences or these deviations to be and find that they are actually very low, then we can conclude to say that as much as there is variability, but we have low variability. We would like our data to be always having low variability. That way, we avoid having any form of biasness. Now, the mean absolute deviation. Now, the mean absolute deviation is a summation of the absolute differences between each value and their mean. Now, absolute difference, meaning you first of all you subtract the value, its value minus the mean, and then you find the absolute value. Now I'll explain later what the absolute value means. So this is the difference between the individual value xi. Remember what we talked about xi in our first video. Xi then minus mu or minus the population mean. Now the absolute difference now, we simply put the absolute value. But what are these two lines? Now let's explain. I'll explain using a calculator as well. Now we're talking about absolute difference. What do you say? Let's say, for instance, our observation was 8 and our mean was 10. Now, the absolute difference says I have 8, which is my x, minus the mean, which is 10, and then what do I have? The absolute value, 8 minus 10 is negative 2. Now, this is where the absolute value comes into play. Absolute value now simply says, if it's negative, then make it positive. But if we had, for instance, 18 and the mean 10, then we would have 18 minus 10, and then 18 minus 10 is going to give us positive 8. And if on the first side we said, if it's negative, make it positive. But here we say, if it's positive, keep it positive. Meaning, the difference between each value of x and the mean will either be 0 if they are the same or equal, or it will be positive, but it can never be negative. So let's do that using a calculator. Now we say shift absolute, here 8 minus 10. Now 8 minus 10 we know to be negative 2, but once we put the absolute value sign there, it becomes positive 2. Now again, if we have 18, then once we put the absolute value, it remains positive. If, for instance, we have 18 minus 100, once we put the absolute value sign, it becomes positive. It's supposed to be negative because 100 is bigger than 18, but because of the absolute value sign, it is positive. So absolute value just simply says if the difference was negative, make it positive. If it was positive, keep it positive. Now, this is referred to as the absolute deviation. Meaning, of course, as we said, deviation is just how far apart is it from the moon. But once we have the absolute value, we call it the absolute deviation. Sorry. Now, the mean absolute deviation, the mean is a summation of values divided by the number of the values you summed. Mean absolute deviation is the summation of the absolute deviations divided by the number of the absolute deviations you've summed. So this is the formula. You will sum n absolute deviations. Therefore, this becomes the mean. Remember, the mean is made by sum over quantity or number of observations. That's why we call this the mean absolute deviation. Now, of course, xi is the ith value that you've observed. Nu is the mean of the data. In this case, it will be a population. And n is the number of observed values. Now, again, just a quick reminder, this represents the sum of values from the first value, this is where we say I equal to n, to the last value where I is equal to n. The following steps can be followed to calculate. Step 1, calculate the arithmetic mean, because how will you subtract from each value if you don't know the mean? Now, of course, it's mu for population, x bar for sample. Then you determine the difference between each value and the mean that you've calculated in step 1. Then you find the absolute value of each difference that you've determined in step 2. And this keeps the positive difference and make the negative difference positive, as I explained about what it means to have an absolute value. And then you add the absolute differences. You divide that by n, that is the number of observations, and you are done. Take an example. Consider the data here. Now we've got 7, 8, 10, 12, 16, 16, 20, which is the data that we had. The total is 89. Now, if you were to have xi minus mu, when you add these differences without the absolute value, you will never go anywhere. All you will get is a 0. That's why we need to remove these negatives. So we need to remove these negatives and keep these positives so that we do not have this 0. We do not want that 0. That 0 takes us nowhere. Now, on this side, we've got xi minus mu, where now the absolute value of negative 40/7, we just simply remove the negative and then we have positive. This absolute value of negative 33/7, we just simply remove the negative and get the positive, and we do the same thing for 7, do the same thing for 5/7, and then we've got these values. And you keep the positive ones positive, so that when you add these positive or these absolute differences, then Then we have this. Now, the mean, step 1, is calculated, and we have this. Step 2, we want the total. The absolute differences is this. The number of observations is 7. Then when you add all these values, you have 194 over 7, which is going to be that. Therefore, the deviation, or approximately 27,714, which is what we have here, of course. Now, the smaller the answer, the less variation or deviation from the mean we have. Remember, I said we want the difference to be as close as possible to the mean, if it is possible. Our data, because it will be random meaning unplanned, because it will be unplanned or not manipulated, we don't know what type of values we will have. Therefore, we don't know if they will be closer to the mean or away from the mean. All we know is that we will have values. So we want the smallest variation or deviation as possible. Let's take another example. Now we've got 7, 9, 8, 9, 10, 7, 8, 9, 10, 11, 12, 13. Their sum is 70. Now we've got the difference, -3, -2, -1, 0, 1, 2, 3. And then we have that. We simply remove the negative, got 3, negative, got 2, negative, got 1, and then the positive remain positive. And then when we add all these values, what we have? 12. And then we just simply sum, so that we have 1,714, and that is it. This is how easy it is to calculate the mean absolute difference. Now, of course, we do know the huge difference, but then again, data is not always going to be the same. Just because one is bigger than the other, it doesn't mean one has more variation than the other. But it's something we will discuss when we do coefficient of variation in our next video. For now, let us stop here. Thank you.